Alright, today we'll be deriving the vorticity equation and then the divergence equation. So in a previous video I showed the derivation for the momentum equation, and that equation has a left-hand side and a right-hand side. The left-hand side is the total derivative of velocity. Here I've kind of changed my notation a little bit. The v vector is now defined as vx, vy, vz. You can also write it as u, vw. But I'm mainly doing this so I don't get confused with w and omega. So this total derivative can be expanded as a local derivative plus a advection term of velocity. And there's actually a vector identity which says that the advection term is 1/2 the gradient of the magnitude of v vector plus the curl of velocity vector cross product with the velocity vector. And this magnitude term, if you write it out, it's vx squared plus vy squared plus vz squared. That is essentially kinetic energy if you include the 1/2. So it's essentially the gradient of kinetic energy. And this term here, we define it, we call vorticity, and we just define it as this omega. So if we then combine everything that we wrote here, can take this term, that's the same, that stays the same. I just plug in this omega, so it's omega cross v, and that's equal to some right hand side that I did another video, and that right hand side is equal to this. So it's I believe there's something to do with centripetal acceleration. This is gravity, which also includes centrifugal. This is the pressure gradient, and then this, I just put every other term that I don't want to deal with inside of this thing called F, and that will include Coriolis and friction. Those are the only other two forces. So throughout here, you'll see, I'll just quickly replace that. You'll see this, and that is a vector. So now I just moved some things around. I put this on the left-hand side. I subtracted these, so now everything's on one nice term. I did some combining where you combine this term and this gravity term. You can kind of use a little like math trick. You invent this thing called the geopotential, which is just g times z, and you'll note that the and you can define gravity as positive or gravity as negative. So I just want to make things nice to get a positive here, so I'll just define it as negative gz. That's just because I defined g as negative, so I can make this positive. Some people write minus k hat g. And so if you take the gradient of both sides, or the negative gradient of geopotential is just gravity. So then, and also this gradient term and gradient term, you can distribute the gradient like if you have a vector like this, you can say that's equal to the gradient of A plus the gradient of B. So I can combine that into one term. Additionally, this term and this term, if this subtracts to this side, then I just wrote them together, and then you can actually take the cross v. So here you have a cross v, here you have a cross v, so it's w plus 2 omega vector cross v vector. And I'll show you what this omega vector is later, but this is actually defined as something we call omega A, which is non-inertial vorticity. So this is vorticity, this is inertial vorticity, and then together it's non-inertial vorticity. And I'll show that in a second as well. So now that I made that definition, it looks like this. Now we want to solve for the curl. What we want is omega is equal to the curl of v. We want this. So to get that, we want a tendency of it. So to get that, we take the curl of both sides of this equation. And sorry that the u's are sometimes not what I had written earlier, but it's the same thing, essentially. So you take the curl of both sides, and essentially what happens is you have d dt of, curl of dv dt, the curl goes inside, so you can take the derivative out, and it's curl, and then that is just omega. So you have the local derivative of omega is equal to the curl of velocity vector, which, yeah, that's true, right? Now the curl applies, distributes, just like with the distributive law, to this term, but the curl of a gradient of a vector, or I think anything, is 0. So that's why this is 0. Just applied the gradient to this term here. I applied the gradient to this one, and then I apply the gradient to this source term that of basically other terms that I didn't want to deal with. Now this term you can split up into a bunch of terms with another vector identity, which you can actually look up on Wikipedia. They have all of them. Wikipedia vector calc identities. And so you have a bunch of terms here. One of them is a curl, divergence of a curl, which is also 0. So you can say this is 0. And another thing is we'll have this term, which can combine back with this term because this is just advection. So you use this and it'll combine into a total derivative again. And then this term, there's another identity which you can basically make it like this. So I'll just do it here. The curl of, it's basically the curl of a scalar times gradient of a vector. It will end up looking like basically what we have down here. Cross P. So it's just the cross product between the curl of each of these two things. Oh, this is this also works between two scalars A and B. But also the same thing will work if you have like a vector B or A or whatever you want to call it, A. Same thing will work. You have a similar situation. Just replace whatever P is. If it's a vector, it's a vector. And so this is what we get. We have essentially 4 terms that lead to vorticity, increasing or decreasing. Basically, if you want vorticity to be increasing, which means it's becoming more cyclonic, which is this way, you need this term to be positive, this term to be positive, this term to be positive, etc. So this term is called stretching or twisting term. At this moment, I'm not sure how to visualize why it's stretching. This is called divergence because this is divergence. And then this term we call baroclinic generation, and essentially this is maximum when the gradient of this one, density, and the gradient of pressure are, I think, at a 90-degree angle is when they're the strongest. And the reason for that is because I'll just write it like this. The reason for that is because if you have a curl of two vectors, it's equal to, by the definition of curl, the magnitude of A times the magnitude of B times sine of theta, where theta is the angle between A and B. So if you remember sine of 0 is equal to 0, and then sine of 90 degrees is equal to 1. So these two are the strongest when you have curl that is the curl of these in a different direction. So maybe we have pressure like this. So pressure 1, maybe the pressure, maybe it's 2 times the pressure, then 3 times the pressure. So the gradient would go from, in this case, from low to high. So this would be the gradient of P. But then if you, at the same time, you have, imagine that these three are now overlaid. This one is, so let me think, 90 degrees. 90 degrees, let's do it this way. So row 2, maybe this is 2 row, maybe this is 3 row. And the gradient would be this way. So now, if you look at these two next to each other, this is gradient P, this is gradient rho. Sorry, this is gradient rho. Then, if they're at 90 degrees angle, this is the strongest. And the reason why it's called baroclinic is just, baroclinic happens when anytime you have temperature or density. So this is specific volume, which is the inverse of density. So whenever you have density or oh yeah, I'm sorry, I called these density, they should be alpha, because then it would be the opposite direction. So alpha gradient. Okay, well, my mistake, but yeah, it's the inverse. So baroclinic is when if temperature just stays the same everywhere, it's called barotropic. But if temperature is changing, so you have like a gradient field where temperature is, changing, maybe it's 2T, whatever. That's not going to happen, but but anyways, if temperature is changing, and temperature is actually related to density by this equation, P equals rho RT. So rho is equal to P over RT. And so alpha is RT over P. So they're related. The gradient of alpha is proportional to the gradient of temperature. So that's why we're saying it's baroclinic, because this would only happen if this term is non-zero. If it's barotropic, then this term is 0. So that's how that works. All right. You can also take the vertical component of this equation by multiplying this k out, and you'll get your own little equation just for the vertical component of this vector that we had before, omega w, and it also has a divergence term and all that kind of stuff. But really, you just need to know this equation, that it will become more cyclonic if you have convergence, which this is divergence, but negative divergence is convergence. So to make this term positive, you would just need this term to be negative, because negative times negative is negative, and a negative of this term is convergence. So if you have air converging into a region, then you should have an increase in vorticity cyclonically. So it's maybe it's like somewhat cyclonically, and now it's like more cyclonically. I guess you can think of it like that. So yeah. So just to save time, I'll make another video for the divergence equation. So if you're interested in that, just check out the next video. Thank you.